All right, so in this section, we're going to be taking a look at a topic that is sometimes your book refers to it as entropy and Gibbs energy. Other books refer to it as just thermodynamics. And just to give you some perspective of where we've been and what we've discussed so far, at the beginning of the semester, we talked about chemical kinetics. And chemical kinetics was a study of how fast reactions happen, how quickly reactions occur. We then took a deep dive into chemical equilibrium, which was a study of the extent of reactions. So do they go all the way to the right, fully to completion? Is it an equilibrium, etc.? So the extent of chemical reactions. Now, in thermodynamics, what we're going to be taking a look at is a question that needs to be answered even before all of these, and that is, will the reaction occur in the first place? Okay, so we've talked about whether reactions will happen fast or slow. We've talked about whether reactions will go to completion, so kinetics and equilibrium, respectively. Now we'll discuss whether or not that reaction will actually happen in the first place. Now, with this discussion, we're not going to talk about how quickly or the extent. We're just going to say, yes, this reaction is favorable. It should occur, or it shouldn't occur. Right? That's really the basic question that we're going to answer in this section. So the first thing we need to talk about before we get into any detail here is to, first of all, define what spontaneous and non-spontaneous processes are. So a spontaneous process is one that does occur under a specific set of conditions, right? So we refer to that as spontaneous under those conditions, whereas a non-spontaneous process is one that does not occur under a certain set of conditions. So, for example, you have encountered some of these spontaneous and non-spontaneous processes before. You know from experience that if you have a block of ice at room temperature, so room temperature is, let's say, around 25 degrees Celsius, you know that that ice will melt, and it will melt spontaneously. You don't need to provide any extra energy for that to happen. However, you know that if you have water at that same temperature, around 25 degrees Celsius, you know from experience that that water will not freeze at that temperature. So it's not spontaneous at 25 degrees. In other words, it is non-spontaneous at that temperature. Other examples include things like a ball that is at the top of the hill, right? A ball will roll down the hill, but you do not expect a ball to spontaneously roll up the hill, right? That would be non-spontaneous. You actually need to provide some sort of energy to get that going. Similarly, in contrast to the first example, if you have water at negative 10 degrees Celsius, it will spontaneously freeze. However, ice will not spontaneously melt at that same temperature. It will stay a solid. So spontaneous versus non-spontaneous processes, we need to know the difference between those two terms. Now, if we take a look at how different thermodynamic or how different quantities are related to the spontaneity of a particular process, we are going to draw on a concept that we actually saw back in General Chemistry 1, and that is the idea of entropy. So before we get to entropy, let's think first of all about a concept we also saw back in Gen Chem 1, which is the a measure of the enthalpy of a system, right? So remember, we talked about, and again, you have to go back and check your notes, but we did talk about delta H, right, which is our enthalpy for a process. And generally, what we're going to see is that a process that results in a decrease in the energy of a system, in other words, exothermic with respect to enthalpy, often is spontaneous. So for example, methane, the fuel that you have in your stove at home, can react with oxygen to produce carbon dioxide and water. The delta H for this is a negative value. That tells you it's exothermic. This process is spontaneous. Now, obviously, if you just have methane out in the open and exposed to the air, it will not happen at any appreciable speed or rate that will allow you to see that reaction happening. You need to provide a little bit of energy itself to get that reaction going. But this is a spontaneous process. It doesn't tell you anything about the speed of the reaction, but it is spontaneous. Similarly, liquid water turning into solid H2O, that is also an exothermic process. We have delta H here at negative 6 kilojoules per mole. This is at a temperature greater than 0 degrees Celsius. And that is exothermic as well. If you had a system or an example, or let's say we had a water or H2O solid, so this is ice, turning into liquid H2O, so that's a melting, right? The delta H for this process is positive 6.01 kilojoules per mole. Okay, this process is endothermic, yet it is spontaneous at temperatures above 0 degrees Celsius. The opposite process, where liquid water turns into solid or ice, right? This has a negative delta H because it's just the opposite of that. So this is exothermic, yet it is not spontaneous. So it's non-spontaneous at those same temperatures, right? We don't expect solid water to turn into ice at temperatures above 0 degrees Celsius. So the point here is the sign of the delta H alone, whether something's exo endothermic, is not enough to predict whether a reaction or a process is spontaneous in every single circumstance. We need to invoke something else, an additional term or an additional characteristic, in order to study the spontaneity of reactions. And that term, that characteristic, that property is known as entropy. So the entropy of a system is a measure of how spread out or how dispersed the energy of that system is. Another way of thinking, and this is not the best way to think of it, but it is an alternative way to think about it. You can think of entropy as sort of a measure of the disorder of a system. But the better way to think of it is how spread out or how dispersed the system's energy is. So more or higher entropy is abbreviated S, means the energy is more spread out or dispersed. Another way of thinking about it is the system is more disordered. And there are lots of things that can contribute to the entropy, an increase or decrease in entropy, for instance. And we'll take a look at how these play here in a second. So if I have this example shown on here, I have a box, there's a barrier in the middle of the box that separates these. Let's say these are gas particles on one side. And then we lift this barrier up now. What we will notice is that these gas particles will spontaneously spread out. And as a result, the energy of the system then is more dispersed. Right? We don't expect, just intuitively, if we lift this barrier up, we don't expect these gas particles to stay on this side. Right? We don't expect them to all congregate on one side. They will start moving around just to the inherent nature of gas particles. They will spread out, the entropy increases, and as a result, the energy of that system is more dispersed, and that happens spontaneously. So what we're going to see is that the spontaneity of a system is actually favored by an increase in entropy. Okay, so if there's an increase in entropy, we can say that that reaction, that process tends to be spontaneous rather than non-spontaneous. So spontaneity is favored not just by a process being exothermic, as we saw before generally. Spontaneity is also favored by an increase in that system's entropy. So whether it's the enthalpy change, delta H, whether it's the entropy change, or maybe it's both of them, in order for a process to be spontaneous, something has to favor spontaneity. So there is as in most cases, there's a mathematical description that describes what entropy is. So entropy S here is equivalent to the product of this constant K, which is known as the Boltzmann constant, 1.38 times 10 to the negative 23 joules per Kelvin, times the natural logarithm of W. And W here is the number of energetically equivalent ways to arrange the molecules in a system. So a number of different arrangements, or we can say the number of energetically equivalent ways to arrange the molecules of a system. Sometimes you'll see this in different textbooks. W is sometimes referred to as, so it's also called microstates. Right, and those are just energetically equivalent ways to arrange the particles. They don't have to be molecules, they can just be particles. So let's change this to arrange the particles of a system. Now, W itself, the number of microstates, sorry, can be defined as X, which is the number of cells, or just cells you can think of as the number of places or smaller spaces in a particular volume, and then raised to the power of n, and n is the number of molecules that you have in there, right? So it's X, the number of cells. Let's say I have a volume like this, and if it's broken into two different, each of these would be a cell, right? So this is one cell, and this is another cell. So for example, when we go up here, right, we had or different cells within that that volume that we were defining. So in the case of having two molecules and having two cells, right? There are different arrangements that those molecules can adopt. We have here, two possible one possible arrangement, another arrangement. We have a fourth arrangement that can be done with those two particles. We have two different particles in this system. As we increase the number of cells, okay, obviously now what we have are different, more possible arrangements as the number of cells increase. We have the same number of particles, two particles. As the number of cells increases, the number of possible arrangements increases as well. The most probable state of that system has the largest number of arrangements, right? And that's something that you'd want to keep in mind as we start looking deeper at entropy.